Okay, so in this video I want to talk about shock pistons and how you would decide which type of shock piston you would select for a given setup. I had been meaning to do this video for a while, but I wanted to make sure I got the physical concepts correct before making this video. So there are two types of damping that a shock piston has an effect on. There's fast damping and there's slow damping. Fast damping has to do with what we commonly refer to as pack. You may have heard that term in the pits, among your racing friends. I'm going to try to explain what pack means. So if you have a fluid, it could be water, it could be oil, it could be air, moving along a boundary. Let's suppose this line here represents a surface. We would generally expect the velocity of the fluid along right at the surface to be 0. And then as we move incrementally further away from the surface, the velocity increases and approaches the, you can call this the free velocity or the main velocity of the gas or the fluid or whatever at an infinite distance away from the no-slip boundary. Okay. Now, this distance between this no-slip boundary, this surface here, and some point in space where we have velocity that's substantially the same as the sort of free velocity, if you want to call it that, this is called the boundary layer. Okay, typically expressed as a term delta. Now, what happens is the rate at which this velocity changes as you move away from the surface here will affect something called shear stress. Okay, so let's imagine that we have a shock piston. Okay, and let's say this is our shock shaft. All right, and let's say we have 2 piston holes and we have fluid flowing through these holes. Okay, so this piston is moving up and down. All right, so let's take a 2D cut across one of these holes here, and let's assume these are normalized velocities and spaces here. So at -1, we're over this edge here of the piston hole, and at +1, we're over this edge here of the piston hole, and at 0, we're right in the middle of the piston hole. Okay, and you can, if you were to plot the normalized velocity of the fluid moving through this piston hole, it would kind of look something like this, kind of like a bell-shaped curve. Okay, and the slope of this curve at any given point in space will determine what the shear stress is within this fluid. And the shear stress plays into an effective resistance. So what that basically means is as I try to move this piston up and down at a higher rate of speed, the difference in velocity, if we want to be really, really simplistic about it, the total difference in absolute velocity between the peak velocity here and at the edges where it's 0 increases. Okay, so we could just draw like a straight line here. And as this difference in velocity increases, the shear stress within the fluid increases, which means we have a higher resistive force within this fluid. Okay, another way to view it is to say that if we want to move this piston up and down at a particular speed, it will require a particular amount of force, and that force depends on this gradient here in addition to the viscosity of the shock oil. Okay, excuse me. Now, this effect here is taking place around all of the open surfaces here that you have, not only the top surface of the shock piston, but also the sidewall, the inside sidewall of the piston holes. Okay, so basically this shear stress effect is velocity dependent, and it results in what we call pack. And pack happens when, if you're landing off of a jump, or if the car is driving on a bumpy surface and there's a lot of high frequency inputs into the shock that try to push the shock piston up very quickly. This results in this, it causes this shear stress condition to happen, and it results in an increase in resistance of the shock dampening action. Okay, so if you have, say, a higher viscosity shock oil, if you go from 25 weight to 35 weight to 45 weight, for example, all else being the same, you will end up with a higher amount of pack in the shock, which basically means that your high-speed damping is higher. Okay. Now, the number of piston holes that you have and the size of those piston holes will affect the relationship between high-speed damping and low-speed damping. Okay, low-speed damping is just, when you're moving this shock up and down at a low rate of speed, or the shock piston rather, and that would happen, when the car is cornering, for example, and the chassis is rolling from left to right. The shock is kind of moving up and down at a relatively slow rate of speed compared to landing off of a jump or going over a very bumpy surface. Okay, so we can very broadly say that low-speed damping depends on the total area that you have in your shock piston opening. Okay, and the high-speed damping, your pack, depends on the perimeter, the total perimeter of all of your shock piston holes. Okay, so if you look at 1/10 scale big bore shocks, whether it's Kyosho or Team Associated or Team Losi, they generally offer the same or substantially the same menu in the types of shock pistons. So you can have a 2x1.5 millimeter hole. So you have two holes that are 1.5 millimeters in diameter each, 2x1.6, 2x1.7, and then you can have three holes by 1.4, 4x1.3, and 5x1.2. Okay, so the total top-down open area for either of these cases is written down here in this table, and the total perimeter of these shock holes is written down here. So if we plot the total area versus the total perimeter, okay, we get these 6 points here. So if I keep the number of piston holes the same, I have two piston holes, and I just increase the size from 1.5 to 1.6 to 1.7. I'm moving along this curve right here. Okay, so I'm increasing the total area, which means that my low speed damping for cornering is lower, so the shock is effectively lighter. Okay, and at the same time, the perimeter, the total perimeter, is increasing. So my low speed damping, as I move along in this direction, low speed damping drops, and as I move along this direction, high speed damping or pack increases. Okay, so basically I'm moving along a particular curve for low speed damping and high speed damping. So as I go to larger piston holes, I have both smaller low speed damping, so it gets effectively softer, and I have more pack, more high speed damping, okay, along this curve. But then I start changing the number of holes and the size of the holes at the same time. So instead of moving along this curve, this would be sort of my two-hole curve here, if I just went infinitely back and forth along this curve. Now I go to 3 holes or 4 holes or 5 holes. Now I'm moving up this way, okay? So your 3-hole curve might be a parallel line like this, 4 holes and 5 holes. So what this effectively means is, suppose I'm on a very smooth surface where it's not bumpy at all, and most of the damping takes place either when I'm negotiating a corner or when I'm landing off of a jump. Okay, if I'm negotiating a corner, that's just my low speed damping there. But the only thing that's impacting high speed damping on a smooth surface is when I'm landing off of a jump. Okay, now if the surface is smooth and say relatively high traction, I might run the ride height rather low, or I might run a relatively low amount of droop on the suspension, which means my total suspension travel will not be as large as if I were running on, say, a bumpier surface. That means with less total suspension travel, okay, I have less space to absorb the energy of a landing off of a jump, which means I might want to run thicker shock oil and or use a shock piston that gives me more pack. Okay, so I can do that by going toward a larger number of piston holes in my shock piston menu here. Okay, so that will move me along this curve here. I can get quite a lot more pack with a 3, 4, or 5-hole piston than I ever could by just taking a 2-hole piston and increasing the piston size. All right, so for the same amount of low speed damping, I can achieve higher pack with more piston holes. Okay, so that's all this is really doing for you here. So again, if you're on a smooth surface, you might tend to want to run something like a 4x1.3 or 3x1.4, something, here, greater than 2 piston holes to give you a bit more pack, but also a bit more, compliant low-speed damping here for cornering. But if I'm on an outdoor track that's very bumpy, then the high-speed damping is not just impacted by landing off of a jump, but it's also impacted by having to, the car go over this really bumpy surface. So I might want to have less pack to allow the suspension to absorb all those high-speed bumps. So I would go to a 2-hole piston here, okay, and maybe go to, and then within this 2-hole piston range here, there's not that much of a difference in pack, okay? So then as I change the piston hole size, what I'm primarily modulating here in the 2-hole piston range is my low-speed damping, okay? So maybe I go to a 2-hole piston that has a larger piston hole size to give me, a bit more of a plush suspension, during cornering, but to also have, plenty of or less pack to handle high-speed bumps. Okay, now the price you pay for using a piston like this is that you tend to suffer in jumping performance. So if you're on a bumpy outdoor track that has very large jumps, then you're in trouble, right? Because you need to compromise either the setup or your driving style. I might use a 2-hole with a large piston size to give me, relatively low pack, but I will end up suffering in the jumping performance. So when the car lands, it's going to bottom out. Okay, well then maybe I can increase the amount of droop that the suspension has so I get more suspension travel. But if I increase droop, I'm increasing weight transfer from side to side and forward to backward during cornering and acceleration and braking. So there's some kind of compromise that you'll have to make on an outdoor track. Okay, but I want to give you a sense of, just very basically speaking here as best as I can, what it means when you change the piston hole size and the number of pistons. Okay, so generally speaking, more pistons give you more pack, and at the same number of pistons, as I change the piston hole size, I'm modulating the low speed damping. Okay, so I hope this makes things relatively clear, and if you have any questions, please post them in the comments. And thanks for watching.